Hello, I think it's audible and everything fine, yeah. Hopefully. Okay, let's wait for 5 minutes. Hopefully, students will join and then we can start. Yeah. So, body lingam diagram, thermite process, coordination chemistry, crystal field theory. Okay, that's cool. We can finish it up. Yeah. सॉरी सर, थैंक यू सर, आप आ गए। ठीक है, बिस्किट नहीं चाहिए। ठीक है, मैं गया। Hello guys, am I audible?
Yes, sir.
Yes, sir.
Yeah. So I think we can start the session. Yeah. I think my slides are visible, right? To everyone?
Yes, sir.
Yes, sir. It's visible.
Okay, that's cool. So our session is for 2 hours. So as you guys know that Google Meet only allows for 1 hour. So at so just 10 minutes before this session, I will share a other link so you guys can join. Then also, if there is any problem, hopefully it should work out because last time there was some problem in the Google Meet, but hopefully this should work out. Yeah. Okay. So let's start the session. So the course is basics in inorganic chemistry. So this is the week two tutorial session or problem solving session, and I'm Hirak. I'm a PhD student at IIT Bombay under Professor Devruta Mighty only. And so this session will be basically on whatever the assignments you guys got for week two in this course. So I will solve a few questions somewhat related to those assignments and try to figure out together how to solve the problems in a logical way. So let's start on. So basically, this week two courses, the main topic was I think Illingam diagram, crystal field theory, and PVT, and I think thermite processes. So those questions will be based on those topics only. So the first question that I have shown in the screen, I think everybody is able to see my screen, right?
Yes, sir.
Okay, that's cool. So the first question is, why is Illingam diagram is used for, or for what purpose we use Illingam diagram? So these are few options that I have given to you guys. So can any of you tell me what should be the correct answer and give a logical reasoning to it? Or you guys can type in the chat box as well. Still students are joining. Okay. Yeah. So the Illingam diagram is basically a diagram of delta G that gives free energy versus temperature. So it is basically used for knowing the feasibility of any reaction in reducing any metal and making a pure metal out of it. So like in a industry, getting a pure metal is much more important because we don't want impurities and we want to use it for further applications. And the most efficient way of doing is by reducing the metal from its oxidized form. And Illingam diagram is one of the very best ways to understand which metal to use and why it is used economically, and like why we should use any metal or any to reduce other metal. So with the help of Illingam diagram, we can select a proper reducing agent that is carbon or carbon monoxide or aluminum for the metal compound. So I have shown this typical diagram where you can see a Illingam diagram, and I have shown you an example. So you guys can see here that just a minute, the pointer is, yeah, it's okay. So you guys can see here that let's say this line, blue line, is for copper to copper oxide, and this line your is for magnesium to magnesium oxide. So you can see that from these two lines that the delta G value for this magnesium to magnesium oxide reaction is more negative as compared to the copper to copper oxide. So that means the second reaction, that's B reaction, is more feasible or more easily going to happen as compared to copper getting oxidized. So the main thing is magnesium so is going to get oxidized more readily as compared to copper. So that means you can use magnesium as a reducing agent to get your copper, to get your pure copper. So and you can see in this final reaction, basically you have to uh, add these two reaction and you will get your final reaction, and you will get the delta G value. So the net delta G is minus 500 kilojoules. And so if the net delta G is less than 0, that means the reaction is feasible, and if the net delta G is positive, that means the reaction is not feasible. So that's the very basic idea of a Lingam diagram that I have shown you. So I think it's clear to everyone, right? And am I audible?
Yes, sir. Audible, sir.
Yeah, that's cool then. Okay. I hope nobody is typing anything in chat box. Let me see. Okay. Okay, that's cool. You guys know anyway. So in this session, what I will do is initially discuss the questions that I have designed for this session. And if I have some time, I will also discuss the previous session's questions because there was some problem in recording and the Google Meet. So I will try to discuss them also briefly. So this is the Illingam diagram. So the question is, what is the incorrect statement for Illingam diagram? Okay, I think I have to remove this one later. Okay, yeah, I think this time it should work out. Yeah. So the question is, what is the incorrect statement for Illingam diagram? So the first option is it's a graphical representation of standard free gives the free energy change with temperature. Obviously, that's true. I think you guys know. And the second is the graph of metal oxides generally move upwards with increasing temperature. Yeah, definitely. That's what I have shown you. And then it represents thermodynamic and kinetic feasibility for the process. And the fourth one is a steep rise in the slope indicates the phase change. So what do you guys think about should be the correct like so guys you guys can figure out to reduce it like what are the correct statements. Obviously first one is the correct statement that it's a gives free energy change and uh, with temperature graphical standard gives free okay, so it's I think not gives free energy, we have written it's only free energy change, so that's the incorrect statement. So it's a gives free energy is your delta H I think, yeah. So you can see this diagram. I have shown you the whole diagram. You can see an example that as we go, just a minute, yeah. So for the graph of metal oxides, it generally move upwards. Definitely, you can see from the diagram is all are moving upwards, and it represents the thermodynamic and kinetic feasibility of the process. Yeah, definitely, it represents the kinetic and thermodynamic feasibility because you can know from the gives free energy change. And then the steep rise in slope indicates the phase change. Obviously there is a phase change when you go from metal to metal oxides on, and also with temperature they will start. So you can see there are some boiling points, melting points written here, and you can understand that there is a phase change also when you move to higher temperature. Definitely it should be. And so I think it's clear to everyone, so we can move to the next question. Other if anyone has any question till the first two questions, then please let me know. Okay, let me check the comment section. Okay, so somebody are confused with D and C. That's just okay. I think it's clear, right, everywhere to everybody. Someone are missing with D and C, but why? What's D? It's just obviously C is correct and D is also correct, yeah. But they, here I have not written gives free energy, yeah. So that's why it's incorrect, yeah. Okay. So the next question is which of the following does not have a metal carbon bond? So it's a question about a little bit about understanding of metal carbon bonds and from the valence bond theory, crystal field theory. So if you see the first question, that's the first option, that's a platinum complex, and you can see there is so this is basically what an olefin, obviously an alkene, C2H, so that's ethane, right? That's ethane, not that's we can say double bond, so it's ethylene, and you have a complex, and next one is the Grignard reagent, obviously ethyl magnesium bromide. C is a nickel carbonyl complex, tetracarbonyl complex, and D is a aluminium tetra ethoxide complex. So which does not have a metal carbon bond? So can anybody let me know which one should be the correct option of all these three, all these four? Just type in the chat box or which one should be the correct one. Obviously C option should have a metal carbon bond because that's basically carbonyl. So carbonyl always the carbon is the atom which directly bonds with nickel, and with A and B if you see then, and with D, so I think you guys can easily guess out. Okay, let me see if somebody has some answers. Okay, so they are telling D. Yeah, Narendra, I think it's D. So can you guys know the structure of it? How does the structure of this aluminum complex is? And how are the complex of other? How the structure of other complexes? So if you see about this first complex, that's potassium platinate complex. So there is a olefin, that's an alkene. So there is a metal carbon bond, that's like the olefin is coordinating with the platinum. So that's you have to say it's some sort of metal carbon bond, because this moiety is like total carbon, and it is basically coordinating with platinum. And then if you see the next complex, that's the Grignard reagent. Obviously, Grignard reagent is a directly metal carbon bond with magnesium and carbon. And if you see the nickel, obviously it should be, because oxygen will never be able to coordinate to nickel because its octet is complete if it has already bonded with carbon. And the last one is the aluminum one, and here the oxygen is going to bind with the aluminum directly, and it's a planar, I think it's a planar complex, because aluminum has only three bonds. It's a planar complex, and you can see the structure. Yeah, that's cool. Okay, let's move to the next one. So due to the back bonding in metal carbonyls, so I think you guys know about metal carbonyls. So that's a metal, and carbonyl, just like this nickel complex, you can see that's a metal carbonyl, nickel tetracarbon carbonyl species. So the strength of metal carbon bond decreases the so when there is a back bonding from the um, so so if you see the bonding characteristic of each of those, so how will the strength of metal carbon bond change when there is a back bonding? Like so initially the ligand, that's the carbonyl, that's going to give its electron to metal, and there will be a back bonding from metal to ligand. So how will the bond distance or the strength of metal carbon bond change? Obviously it should increase or it should decrease. That's the first question. And second is strength of carbon oxygen bond increases. Second is strength of all bonds are unaffected, and strength of the D, C, and D are okay. It's the same. Okay, that's a mistake. Yeah, the typing mistake. So, what do you think? What should be the correct answer? Okay, let me see the chat box if somebody has some idea about it. Okay, Narendra is saying it's B. Okay, other guys think about it a little bit. And mhm. Okay, so if you see the correct of the answer, so that's strength of all bonds are unaffected. So synergistic bonding interactions are present in metal carbonyls. The sigma bond is formed when lone pair of electron of carbonyl carbon is donated to vacant orbital of metal. Definitely, there should be a vacant orbital in metal, and that's usually the d orbital. And to form a pi bond, an electron pair is donated from filled metal d to the vacant anti-bonding pi orbital of the CO. So therefore. Okay, and so there is a anti-bonding pi orbital. Obviously, if you see the molecular orbital diagram of carbonyl, you will find that almost all the valence bonding MOs are already filled, and if you fill any extra electron, that's going to the anti-bonding orbital, and this involves a literal overlap of orbitals, and due to this the electron density in bonding pi orbital of CO decreases, and therefore the anti-bonding pi orbital will increase definitely. So what will happen is the CO bond, that's the metal, yeah, that's the CO bond, and this decreases the bond order obviously. Hence, the strength of carbon oxygen bond decreases, and the strength of metal carbon bond increases. So therefore, uh, the strength of a metal carbon bond will obviously increase because the metal is again giving the electron back to the carbon. But if you see about the CO bond, the strength should obviously decrease because then you are giving the electron to the anti-bonding orbital of CO. So therefore, the CO bond should decrease. So therefore, B is incorrect. And the first option, that's the strength of metal carbon bond decreases, that's actually increase, that's not decrease, because you are giving the electron back to the carbon, and there is a pi bond also extra that's coming out, and therefore the option is strength of all bonds are unaffected. I think there should be other option as well, but I think you guys understand the concept. There is some mistake in options, I think.
Sir, what is the difference between C and the D options, sir? So are almost looking like same, no?
Yeah. There is some mistake in, I think, in my typing mistake, but the question is typically about to understand the metal carbonyl bonding characteristics. So I think you guys understand them. Whatever I was telling is that.
Understood, sir. Understood, sir. Thank you.
Yeah. I say there is some typing mistake, but probably A and B, E should be wrong, obviously, right? And there is some
Yes, sir. Yes,
typing.
yes, sir.
Yeah,
Correct, correct.
there should be some typing mistake. But the main concept was to make you understand about how, if there is a back bonding back to the back from the metal to the carbonyl, then how how the strength of each and every bond changes. Okay, let's go to the next one. Okay, I have already written the answer. Okay, among the following metal carbonyls, the CO bond order is lowest in. So obviously I have given the answer as well, but you guys can justify how why B is the correct answer. So basically, how in all of the complexes, what is the factor that is going to determine the carbon oxygen bond order, or you can say bond strength or bond length? That will be determined by the what number of electrons in the central metal ion, that's magnesium, iron, chromium, or vanadium. And uh, and so how is the back bonding characteristic in each of those complexes is going to determine. So if there is a more back bonding to the carbonyl, so therefore the CO bond order will what, obviously decrease. And if the CO, because then the electron will go to the anti-bonding orbital, and the CO bond order will decrease, obviously, right? So you have to find the complex which is going to give the best back bonding, and that will only happen with the metal that is having the most number of electrons, d electrons, obviously, right? We are, because all those metals are d 3d metals. So if you see about magnesium, so magnesium plus is basically, so you can see the first option, magnesium plus is 3d5 4s1 in presence of Cu. The effective configuration is 3d6 4s0, and there is 3 lone pair of back bonding with vacant orbital to carbon to Co. So you can consider it as a 3 lone pair trying to back bond to the to the Co. And if you see the second option, iron, so that's your, instead of 3 that will be 4, because it has 8 electrons in the, you can say, 8 valence electrons. And about chromium, that's you can consider it as a 3d6, so that's 3. And vanadium, the oxidation state is V minus, so that's also 3. So therefore iron has the most number of electrons, so it will do a very good back bonding, and therefore the CO bond order will be the lowest in the iron case. I think this it's clear to everyone. People are still trying to join. Okay, just a minute. Let me give the link for the next session also. Otherwise, it will be. I'm typing it. I will also join if the meeting shutdowns. If in between, you guys copy the link. If the meeting shutdowns, then please join in this link. Okay. Hopefully, it will shut down not now, but probably in 20 minutes or so. Okay. Let's move on to the next question. Okay, so the next question is which of the following compounds will show optical isomerism? So for that you have to draw the structures of each of it and try to understand which will show optical isomerism. So what's optical isomerism first of all? What is optical isomerism? You guys know about it? People are still trying to join. Huh? Okay, so if you see, optical isomerism is basically about symmetry. So if a molecule is, we can say, very symmetric, then optical isomerism only comes like if you have flow some light to any compound, and how it rotates the light. If it is positively rotating the lights there, or negatively rotating the light, so that will define its optical isomerism capability. So we cannot just shed a light on each of this, right? We have to understand it from the symmetry of each of these molecules. How is each of these molecules, either it's symmetric or anti-symmetric, and from that we can understand which will show optical isomerism and which will not show optical isomerism. So if you see about this compounds, then you will find that um, the first complex, that's is your cobalt, your tetra amino dichloro complex. So if you draw the structure, it will have some symmetry, right? It has some symmetry because you will find a C2 axis, I think, in this case, first option. And if you see about the trans, then the two chlorides are opposite. So first and second option, they are octahedral complexes, right? And if you see in both of the complexes, there is some symmetry. In the trans one, then there will be, I think, a D4H symmetry. There is also a C4 axis going from one chlorine to cobalt to chlorine, and in first one also there is some symmetry. But if you see about the next two complexes, that's third and complex 4, then you will find that they does not have any symmetry as such. So they does not possess this symmetry. So therefore that means that the trans complex exists in an optically active form, and your first option, the first and second option will show some optical isomerism because they have some symmetry, so they will rotate the light in one of the directions. But the third and fourth option, that they doesn't have any sort of symmetry, so therefore they will uh, not show any sort of optical isomerism, and you will not be able to form any other optical isomerism in each of those in the third and fourth options, just like your cis trans and things. I think you guys understand the concept. Okay, let me check once.